Hi, welcome to Unit 4 on probability, random variables, and probability distributions. In this video, we're going to focus on topic 4.4, mutually exclusive events. It's actually a pretty fun video. I mean, take that for what it's worth, right? I think it's a pretty easy concept, and I think doing the math with these problems is actually kind of fun. It makes a lot of sense. Very logical reasoning here, very easy to think your way through. All right, so first let's talk about what's called joint probability. The probability of two events A and B both occurring at the same time or on the same trial is called joint probability. So this is two events happening at the same time, like a boy and they have blonde hair, or a girl who has braces, right? There's a girl, two events, girl has braces happening at the same time. This idea is also known as the intersection of the two events A and B. So we denote joint probability as the probability of A and B. Now, the mathematical symbol for "and" is this upside down U, all right? That actually stands for the intersection. Okay? So that's why "and" or joint probability is known as the intersection of two different events. It's where they overlap, might be a better word to help you understand that. All right, so here's an example. All right, let's assume that there are 36 students in a classroom, and event A is selecting a boy, and event B is a student is wearing glasses, selecting a student wearing glasses. So the probability of event A would be all the boys in the class divided by 36, because that, there's 36 outcomes, 36 kids, and if you're a boy, that's going to make me happy. So all the boys out of 36. Wearing glasses, that'd be the probability of event B. And that would be anyone wearing glasses divided by 36. So 36 are my total outcomes, anyone wearing glasses. So if I pick you and you're wearing glasses, I'm going to be happy. So I would count how many kids wear glasses, all right? So the intersection or the joint probability of A and B would be any student who is a boy and wears glasses. So we're looking at the combination, the intersection of wearing glasses and being a boy. So I'd have to count how many very specific people there are, boys and wear glasses, and again, divide it by my 36 possible outcomes. So a nice way of viewing this is what we call a Venn diagram, okay? V-E-N-N. I'm sure you've seen these before, at least I hope so. So the idea here is that we have these two interlocking circles. So the blue circle is representing getting a boy, selecting a boy, right? And the red circle is wearing glasses. And these two events overlap, which means that they're joined. They're joined together. They're joined, right? So the overlap in the middle here would be both boy and wear glasses. So anybody that meets both of those classifications would be here in the center. Now, to the left here, this is very, very, very specific, right? The entire blue circle is all boys, some of them wearing glasses, and that's what gets overlapped here in this middle area. But here to the far left, these are boys that do not wear glasses. So if you're a boy who does not wear glasses, you would fall somewhere over here because you would not be joined or overlapped with wearing glasses. Now, over here to the far right, these would be wearing glasses, but not boys. I mean, if you really want to get into it, these would be your girls who wear glasses, because they are definitely going to be in the red circle because they wear glasses, but they're not overlapped with wearing a boy. So the entire blue circle, if I just focus on the whole blue circle, those are all boys. Some of them are wearing glasses, some aren't. The entire red circle is everybody wearing glasses. Some of them are boys, some of them aren't. So on the outside of this would be you're not a boy and you don't wear glasses. So if you really want to specifically think about that, that would be a girl without glasses. So this entire box represents my sample space, everything that could happen relating to these two events. I could be in the blue circle if I'm a boy. I could be in the red circle if I wear glasses. I could be in this overlapped if I'm both a boy and I'm wearing glasses, because if I'm a boy without glasses, then I got to go over here. If I'm a person that's not a boy and I wear glasses, I got to go over here. And if I'm neither of those things, then that's when I go on the outside. So Venn diagram is a nice way of actually seeing this joint probability, this joint connection between these two events. Now, the opposite of this would be disjoint. This is also called mutually exclusive. If two events cannot occur at the same time, then they are said to be mutually exclusive. Now, we could also say disjoint, right? But mutually exclusive is really, it's the name of this topic, right? So mutually exclusive is the big word. So mutually exclusive means that the probability of A and B happening at the same time is 0. A picture of that would be two non-overlapping circles, two things that just cannot happen at the same time. Some examples of this: boy and girl. There's no overlap there, right? There's not a person who is a boy and a girl at the same time. So that's why that would be mutually exclusive. Let's just say you take a test, and one event is you get an A, another event is you get a B. That would also be mutually exclusive because you can't get an A and a B on the same test. You can't do it, right? You can get an A, you can get a B, you can't get both an A and a B on the same test. So that would be mutually exclusive. Other examples would just simply be like yes-no things, like smokers is event A, non-smokers is event B. Well, that's everybody, right? You're either a smoker or you're not. There's no overlap there, right? Well, I occasionally smoke. Well, then you're a smoker, okay? You can't go into the circle for non-smokers if you occasionally smoke. So that would be another example of mutually exclusive events. But the idea here is that they don't overlap. So there is a joint probability of, A and B would be 0. They just cannot happen at the same time. So that's really it for the topic in this video. Mutually exclusive are two events that cannot happen at the same time. Joint probability would be two events that do have overlap. All right, so let's look at plenty of examples here because this is definitely one of those topics that you want to watch some examples of. All right. A high school study hall contains 80 students in it. Of those students, 38 of them are on a sports team and 29 are on the student council. There are 20 students who are not on student council and not on a sports team. One student from the 80 will be selected at random. Let S be the event that they are on a sports team. Let C be the event that they are on the student council. And the question is, are S and C mutually exclusive? So mutually exclusive means that you cannot play sports and be on student council at the same time. Not mutually exclusive would be that there's some overlap. There's some kids who are both. And how the heck can I figure that out? Well, I have found the easiest way ever to figure out the answer to this question. And it all involves making a little two-way table. So on the left-hand side here, I'm going to write sports. And do you play sports is a yes or no question. Or are you on a sports team at your high school is a yes or no question. And on top, I'm going to put student council. And are you on student council is also a yes or no question. And then I'm going to do is I'm going to make a little table here. Okay? Make a little table. All right. So here is what I was given. And again, my table's kind of crappy, but sorry. All right, I was given that there are 80 total students. I was given that 38 of them said yes. So yes, I play sports. That's a total of 38. And I was also given that 29 said yes, I'm on student council. So yes, student council, 29 total. Now, the other thing I was told, well, give me one more second. Now, let's think logically here. If 38 kids said, yes, I'm on a sports team, well, if there's 80 kids in the room, then I can imply that 42 are not on a sports team. If 29 kids said, yes, I'm on student council, well, that would imply that 51 are not in student council. That's just simple math. 80 minus 29, 80 minus 38. Now, the numbers on the outside are our totals, yeses and nos for sports, yeses and nos for student council. And now on the inside are much more specific numbers. For example, here is the double yes. And that's my overlap. If there is any kids in here that are double yes, yes, I play sports, yes, I'm on student council, well, then that's going to answer my question for me that these events are not mutually exclusive. If there are no kids in there, well, then I'm going to say, yeah, they are mutually exclusive. There is no overlap. So now how do I figure this out? Because the rest of these boxes are also very specific. For example, this box right here is no, I'm not on either. Here we have, I don't play sports, but I am on student council. And up here we have, I do play sports, but I'm not on student council. Well, the other piece of information is the key. They told me that 20 students are not on student council and not on a sports team. So that's going to go right here. That's the double no. So now, with some simple math, I can figure out everything else I need. All right, I can look at this two ways. 51 kids are not on student council. Minus 20 leaves me with 31. Again, I need that to add up to 51. So same thing over here. If 20 kids are not on student council, not in sports, but 42 total kids are not in sports, I need that row to add up to 42. So that number would be 22 kids that do not play sports but are on student council. So finally, now I can actually find my missing circle here two ways. I could look at the student council yeses. 29 said yes. Well, of that 29, 22 do not play sports. So there's got to be 7 that do play sports. Of the 38 kids that play sports, I already knew that 31 are not on student council. So I have to add up to 38. So that means 7 are yes, I am on sports. So all of these numbers on the inside are very, very specific. But for this video, really the only ones that matters the most to me is the double yes, because that's the overlap. So if S is playing on a sports team, C is being on student council, there are 7 kids who do both. So these two events are not mutually exclusive. Because remember, mutually exclusive means that there is no overlap. These two events cannot happen at the same time. And I just proved with my little table here that it is very, very possible there are, in fact, 7 kids that meet both. So it's really just a matter of making a table and filling it in. It's actually quite easy and very, very, very simple to do. All right, so if you need to run through that again, just kind of hit rewind on the video to walk through it. But it all starts with going into my totals and then filling in the double no that they gave me, and then the rest of it I could figure out. But I do want to add that the other numbers in red here are very, very, very specific numbers. This is 31 kids who, yes, are on a sports team, but no, are not on student council. That is also very specific, right? That is also technically joint probability. This is 31 kids who, yes, play sports, and no, not on the student council. Even this 20 right here is technically a joint probability because it's a combination of no, don't play sports, and no, I'm not on student council. So to answer the question, though, about S and C, it all comes down to that 7 kids. Okay, so that's 7 out of 80 that are both. So there definitely is overlap. All right, let's look at another table here. A sample of 942 homeowners are classified in the two-way frequency table below by the number of credit cards they have. Do you have 1, 2, 3, or 4 or more credit cards? And how many years have you lived into your current home? Less than 1 year, 1 to 3 years, or more than 3 years? All right, and all the numbers in these tables are simply counts of these people. Around the outside are my totals, and on the inside are very, very specific number. Every single number on the inside is very specific. For example, this 19 right here are 19 people who have 2 credit cards and have lived in their house for 1, 2, 3 years. All the numbers on the outside are not so specific because, like, for example, this is 334 people who have 1 credit card. That's it, 1 credit card. On the inside are a bunch of ands. On the outside are a bunch of single probabilities or single counts. All right, so here's the first 2 tasks. Name 2 events that are mutually exclusive and then name 2 events that are not mutually exclusive. Now, are or is mutually exclusive. These are 2 things that have no overlap. So what 2 things have no overlap? Well, living in your house less than 1 year and living in your house more than 3 years. Those 2 things cannot happen at the same time. You cannot meet both of those. You're either in one of those columns or you're in the middle one, I guess, too, right? You can't be in both. If you live in your house, you're going to either say I live in it less than 1 year or more than 3. I mean, you can't go in both of those. So that are definitely mutually exclusive. Another example would be having 1 credit card and having 2 credit cards. They're mutually exclusive. I can have 1 credit card. I can have 2 credit cards. If I have 1 credit card, I can't overlap with 2 because I only got 1 credit card. So those are definitely mutually exclusive events. And you could pick any 2 things that are on the same side, whether it be any of these or any of the ones across the top, and those are going to be mutually exclusive. Not mutually exclusive, remember, not mutually exclusive means that they have overlap. Well, any combination of credit cards and how long you've been living in your house, because all of these, none of them have a 0, well, then they all have some overlap. Even right here, more than 3 years and 2 credit cards. There are 4 people who are in both of those categories. 4 people have 2 credit cards and have lived in their house more than 3 years. So again, any number on the inside can be used to show not mutually exclusive or the fact that there is overlap between those 2 events. All right, so now here's the question. If one person is picked at random from this sample of homeowners, what is the probability the person selected has 3 credit cards and has owned their house for more than 3 years? So I'm trying to find the probability of 3 credit cards, I'll abbreviate, and we use an upside down U to symbolize and, living in their house more than 3 years. Now, I'm classic for trying to abbreviate things, but I hope you guys get my abbreviations. It's pretty simple. All right, so how do I figure this out? Open your eyes and look in the chart. All you got to do is cross them out. 3 credit cards is right here. More than 3 years is right here. So I'm looking right here. The overlap is 20. They overlap more than 3 years. They overlap with 3 credit cards. So that's 20 out of 942 people that are both having 3 credit cards and living in their house for 3 or more years. So it's really, really easy when you have one of these tables to find and probabilities like this, right? What's a little bit hard is when you have to make the table, but when you have the table, it's quite easy. All right, here's another example with a table that's made. 250 people attended a high school basketball game one night. It was recorded what team each fan was rooting for and if they purchased food or not at the concession stand. The table below shows the counts. Consider picking one person at random. So let's look at the table here. We have people who were rooting for the home team, people who are rooting for the away team, people who purchased food, people who not. Numbers on the outside are our totals. Numbers on the insides are our very specific ands, our joints. All right. They want me to find the probability a person roots for the home team and purchase food. That would be 120 people. I mean, you don't have to do any work here. You just got to open your eyes. 120 out of 250 would be the probability that you purchase food and root for the home team. All right, pretty easy, guys. I mean, I really can't make this complicated. All right, next question. What is the probability the person did not root for the home team and did not purchase food? All right, not rooting for the home team implies you rooted for the away team and did not purchase food. So that would be away team and did not purchase food. That overlap would be 30 people that overlap with both of those categories out of 250. I can't get any trickier than that. All right, let's do one more problem here. On Thanksgiving, around the United States, 72% of households have turkey on the table. Okay, cool. 21% of households have ham on the table. 11% of households have neither turkey nor ham. What percent have both? All right, this is actually very, very similar to our sports and student council, but instead of having accounts, we just have percentages. It doesn't actually make it any different. I'm going to make a two-way table here with turkey, yes or no. I'm going to make the top ham, yes or no. All right, now I'm going to just kind of make some lines here just to kind of organize it. Sorry that I'm really poor at drawing things neatly. I'm assuming you get the idea here, though. All right, so what was I told? 72% have turkey. So yes, 72% of people have turkey. The ham, diddly squat, doesn't matter. 72% have turkey. All right, ham. 21% said yes, we have ham. Again, that has nothing to do with turkey, just 21% total have ham. So now there's also 100% total people, right? So, I don't need a total here because when you work with percentages, it's 100%. Now this tells me that 28% did not have turkey. All I do is subtract. If 72% had turkey, 28% did not. If 21% have ham, that means that 79% did not. Again, that's just subtraction. Those are my totals are on the outside. These numbers are all very specific. And, they're specific in the sense that they're just singular. Like this is just turkey. So if all I said was what's the probability that somebody has turkey? Easy, 72%. What's the probability that somebody did not have ham? So no ham, not ham. Well, that's easy, 79%. The numbers on the inside are our joints. There are combinations of these two things, turkey and ham. Well, one of them was given to us. We were told 11% have neither. So that number is going to go right here, the double no. 11% had neither. And once you have that double no, you can fill everything else in. All right, this column right here needs to add up to 79. So if 11% are no, then 68% would have to go right here. So this is 68% that have turkey, but no ham. That's very, very specific. And again, that whole column has to add up to 79%. Now going acrossways here, this row right here has to add up to 28%. So that means we would have 17% right here. This is no turkey and they have ham. Again, that's very, very specific. Because when we just talk about turkey, we don't care about ham. Maybe there's ham, maybe there's not. It doesn't matter to us. It's just turkey. But the 17% is very specific. That's turkey and definitely no ham. So now we just got to figure out the double yes, because that's the question they asked, both turkey and ham. Well, I can look at the column or the row. It doesn't matter. It's 4%. Because I need to add up to 21, so 4 and 17 is 21. I also need to add up to 72, so that's the 4 and 68. So there are 4% of households that have both turkey and ham on their table. All right, now if you're looking for one more way, and most kids love the table way, I'll tell you that much right now. Most kids gravitate towards that table because it's so easy. But another thing you could do is you could make a Venn diagram. So I got turkey right here. I got ham right here. Sorry, my H is there. Okay, I'm going to use a different color there so you could see. Turkey, and here's my ham. Okay, whatever. All right, now here's the kicker. I know that 11% have neither. Those are the people that are left out. And now I got to figure out the insides, right? And that's a little bit tricky, right? So you got to really kind of take your time because this overlap here, this is going to be the 4% that have both. So I'm going to put 4% right there. Now, over here, this is very specific, right? Because the whole circle's turkey. This specific part over here is turkey, no ham. So that's going to be the 68%. Because that way, the whole turkey circle still adds up to 72%, 68 and 4. But the 68% is specifically the people who have turkey and no ham. And then the ham part over here, the whole ham circle needs to add up to 21. So this would be the 17% that have just ham and no turkey. So that way the whole ham circle adds up to 21%, but the 17% is very specific. And then the 11% is the people that are left out. So hopefully that makes sense. All right, one more question, just piggybacking off of this. Let's do the same problem. 72% of households have turkey. 21% of households have ham. What if I told you that 7% have neither? How would that change? Well, I just want to run through this really quickly. Here's turkey. I just want you to see what's going to happen here. This is actually kind of cool. Here's ham across the top. Yes. No. Right at this point, this is like, all right, this is easy. Again, most kids love this table stuff. So 72% like ham. That means 28% do not. Whoa, I said that wrong. 72% have turkey. 28% do not. 21% have ham. That means 79% do not. There's my 100% of people. All right. If I told you that 7% have neither, no turkey nor ham, well, then that means I got 72% right here because I got to add up to 79. And that means I got, let's see here, 21% right here because that row has to add up to 28. And what that means is I got nobody that has both. Because in that top row, I already have my 72% accounted for. So there can't be anybody who also has ham with their turkey. And in this column for ham, I already got my 21% accounted for. So that means nobody could have ham and have turkey on their table. So this would be a case where they are mutually exclusive. There is no overlap. And it was just how the numbers felt, right? Because I did that 7%, when I tried to figure out the no's, I got 72, I got 21, and that was it. Like, I couldn't have any more percentage of people be in the double yes. So again, there are examples like this where after you make the table, you find out that it is mutually exclusive. As opposed to the other example where the only change was it was 11%, it was not mutually exclusive because we did have that 4% overlap. All right, hopefully you guys end up thinking that mutually exclusive is pretty easy. Obviously, you're going to need to do a couple problems on your own to really kind of prove to yourself that you know how to do it. But overall, the concept is pretty simple. Mutually exclusive means that the two events cannot occur at the same time, whereas joint means that there is overlap, right? Not mutually exclusive. All right, guys, that's it. Now time for you to practice and see you in the next video.